So now we're going to look at some more patterns of the different things we can do at the top of the loop, in the middle of the loop, and at the bottom of the loop. And the first one we're going to do is counting. Now we're going to take a look at the number of something, the number of things in our list. Now we could just inspect it and see 6, but you will have for loops like you're reading through a file or scanning through some data. And so the notion of counting, you have to assume that you don't really know, that there's going to be a lot more than just 6. But for now, we're just going to do 6, and we're going to count how many things that we see in this loop. And the pattern is simple. You set a variable, Zork, to 0 at the beginning. We often call this variable count in mnemonic. And now we're going to run this loop 6 times. 1, 2, 3, 4, 5, 6. And each time through, we're just going to add 1 to Zork. So Zork starts at 0, then it goes 1, 2, 3, 4, 5, 6. And we're going to print it out. So, we see the 9 and Zork is 1. See 41, Zork is 2. And Zork is 16 when we see the 15. 4 stops, and we print out afterwards. And this then is 6 is then the ultimate count that we got. So that's very, very simple. The pattern is that set it to 0 at the beginning, add 1 to it, and if you run that enough times, then this is how many times that happened. And in a sense, it's how many times this line ran, right? Sometimes you put this in an if statement, etc., etc., etc. Okay? Oops. Now, we can do the same thing to get a total. And the way the total works is you compute a running total of the number of the items that you've seen so far, and at the end, the running total, in effect, becomes the total. A better variable name for this would be like sum or total or something, but Zork, I'll use Zork again. So you set Zork to 0, and it starts out, the total we've seen so far is indeed 0. And then we're going to run this 1, 2, 3, 4, 5, 6 times, and thing is going to be the iteration variable. It's going to take on the successive values, and each time through, we're just going to take our running total and add to it the thing we've seen. So we see 9, and the running total is 9. We see 41, and the running total becomes 50. We see 12, the running total becomes 62. We get a 3, it becomes 65. We get 74, running total is 139. How many more are we going to see? We don't know. Could be a million, could be 1. Oh, it's only 1. We get a 15, our running total is 154. And what's true at any moment here is the running total is right of what we've seen so far. Now, when we're done, the for loop quits for us, and afterwards, 154 is indeed the total. So the running total while we're in the loop, at the end of the loop, after the end of the loop, we have the actual total. So it's not very difficult to convert this to the average because we've calculated the count and we've calculated the running total, and now we're going to have the average by simply dividing those. Okay, so now this time I've used mnemonic variables. Don't get confused by this. Mnemonic variables are just friendly names I chose for you to read the code easier. I am not communicating to Python in any way by naming this count and sum, but count and sum is nice. Okay, so I set count to 0 and sum to 0. Oh, go back up. I set count to 0 and sum to 0 at the beginning, and the count is 0 and the sum is 0. And then I'm going to run this loop 6 times. 1, 2, 3, 4, 5, 6, and each time value is the iteration variable. I count, every time I run the loop, I count equals count plus 1, sum equals sum plus value, so I have a running count and a running total, and they show up here, 1, 2, 3, 4, 5, 6, and then the running total. And then at some point, the for loop, we do the last one, and the for loop jumps out, and it divides 6, 154 is the count and running total, and then it divides the average sum over count. Okay? So that's just, again, a pattern of something in the beginning, something in the middle, something in the end. Another kind of thing we tend to do in loops is we look for things, we hunt for things. And so this is where we have an if statement inside of a loop, and of course I've created a silly simple thing. In this code I am looking for large values that are greater than 20. And again, don't think of this as just 6 numbers, but I'm looking for all the values and I'm going to print them out. So, it says before, it's going to run this 9. Well, if 9 is greater than 20, it's false, so it goes back up. 41, true, so it prints out 41, then goes back up. 12, false, goes back up. 3, false, goes back up. 74, true, so it runs this, so out comes that little print statement. Goes back up, and then 15 is the last one, and that's false. it goes back up and the for says we're done, and then we do afterwards. And so this is just the notion of having an if statement inside of a for loop, where we're sort of picking or choosing or selecting or looking for something in a large set of things that we're looping through. We can also say, I want to know if a particular value is there. And so we're going to use a Boolean variable. And we've talked about integer variables like 1, 42, and then floating point variables like 98.6, and then string variables like hello world that have quotes in them. This is a fourth type, a kind of variable. It's called a Boolean variable, and it only has two values. It has true and false. Matter of fact, these if statements, they return Boolean values. Value equal 3, that is returning a true or a false based on the value of value. There's a mnemonic confusion there, right? But I'm using it. So I'm going to make a variable called found, and that's a decent name for a variable, so don't get hung up on that. And I'm going to initially say found is going to indicate to me whether or not I found a 3 in my list. And I'm going to start before the loop starts, say false, because we haven't found anything yet. So found equals false. And so at the beginning of the loop, found is false. Before the loop starts, found is false. And now we're going to run this loop a bunch of times. 9, is that true? No, skip. 41, is that true? Skip. 12, skip. Right? So 9, 41, 12. And found has remained false because we haven't done anything to it. But now in comes a 3. And this becomes true. So it runs this code. So found becomes true. And then we print it. And you'll notice that when we see a 3, we get true. And then it runs again. We get 74. It's still false. 15. It's still false. Run, 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 quit. And the residual afterwards is true. And in fact, if you didn't know any of this and you don't print that out, all you know is that afterwards we loop through all those things and we know that there was a 3 in there. That's what we're doing. So we searched all of them, we checked for 3s when we found a 3, and you can see basically that, you know, the found remains false until it flips to true, but then there's nothing to set it back to false. There's nothing in this loop that's going to set it back to false. So once it sort of catches the 3, then it remains true for the rest of the loop, and then it just finds its way out. Now, if you want to think about it for a moment, ask yourself, how might we make this loop more efficient by putting a statement right in here? Think about a way to, once you've found it and it's true, there is sort of no reason to keep on going. So what would you put there to perhaps make this loop to look for 3s, just to tell you whether or not there was at least one 3 in there, how to make that more efficient? Just think about that. Okay, so now let's look back at the largest value that we started out with, right? And so if you think about this, let's kind of give it a sort of a rough look here. Largest so far is our kind of like a running total, but it's our hypothesis is the best large number. And we have this if statement that says if the number we just see right now is greater than the largest so far, then capture it, right? Take whatever number we saw and capture it. So when we see 9, it's better, we capture it. We see a 41, it's better, we capture it. We don't capture this, we don't capture this, but we capture the 74, and we don't capture the 15, and that's how we do it. So you could think of this as better. When the number we're looking at is greater than our working hypothesis of the largest, we grab it because it's better. So this line right here is the grab line. Grab it. Okay? So then the question is, how would you modify this code to teach it to find the smallest value in this list of numbers? Think of it as you have a starting number, you have a sort of what's better in this grabbing notion. How could you do that? Take a look. Okay, so let's take a look. So let's do a couple things. Like if you look at this if statement that's better, well, it's better now if the number is less than. So but then we should probably change this to be smallest so far, 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 right? Matter of fact, that's what this is. We've changed the word largest so far to smallest so far, and we've changed the greater than to a less than. Is that going to fix it? I'll give you a second to look at it. Pause if you need. Is that going to fix it? Is that going to find our smallest number? The answer is, of course, no, it's not. So if we run this code, so we set the smallest so far to -1, and it starts out -1. We run it, and it's 9. Is 9 less than -1? No, it's not. So after we see a 9, the smallest so far is -1. Now we're going to run 41. Is 41 less than -1? No, it is not. So the smallest so far is still -1. As a matter of fact, it isn't the smallest so far anymore. Just because we named it smallest so far doesn't mean it is the smallest so far. It didn't work out so well. And so you see that none of these, because they're never less than -1, do anything. And we claim that afterwards the smallest we've seen so far is -1. And that is because, of course, -1 is smaller than any of the numbers that we saw. So how could we fix this? Well, if we started the smallest so far with some like arbitrary big number, then it'd be better. So if we made this 100, whoops, come back. If we made this be like 100, that'd be good, because the first time through, the 9 would be less than 100, so we would capture the 9, and then the rest of the loop would work just fine. But then what if we didn't know that how big these numbers were? As a matter of fact, the largest so far wouldn't have worked if all the numbers were negative. Think about that. We just assumed they were positive, and so we kind of wrote lazy code that assumed all numbers were positive. That might not be a good assumption depending on the numbers that you're dealing with, right? So maybe 100 is a good number to start with, or maybe like 1,000 or 10,000, or like some number with lots of zeros in it. How big should we make this? And the answer is we're kind of solving this problem the wrong way. And the thing we really want to do to solve the problem is to just accept the fact that if we're looking for the smallest number so far, that the right hypothesis is the first number. And if we just knew what that first number was, the 9, because it's the first number, we know that it's both the largest so far and the smallest so far as soon as you see the first number. But we don't know here before the loop starts what that first number is. I mean, you can look at it, but assume this is just data that's coming from somewhere else, and we don't know it until we start reading it. So we have to construct a loop that deals with the fact that we want to capture the first value as our hypothesis for smallest so far. So how do we do that? Let's take a look. So what we do is we use yet another type. So we have integer, floating point, string, Boolean, and now we have a thing called the none type. None type is a special marker in that it only has one value. Boolean has true and false. You know, floating point has an infinite number of values, and integer has an infinite number of values, but none type has one value, none. None is a constant. Capital none is a constant. The difference is we can check to see if we have stored none. None is often used to indicate emptiness, not non-existence, because smallest doesn't exist until we assign it, but we're going to assign it to like a mark, a flag, a marker, some way to say, oh, this is not even a number, it's nothing. And so we're going to, and you can do this. So that's like makes a variable called smallest, and in it puts none. It sticks it right in. It's not a string none, it's like a special type. Okay? So that actually captures the notion that before the loop starts, the smallest number that we've seen so far is none. We haven't seen any numbers. Okay? So then we come in and we have an if statement. And we have a new operator called is. Is stronger than equal sign. And so if smallest is none, that becomes true. It runs this case. And so then what it does is it copies this first value, which is 9, into smallest. And so we see a 9, and the smallest so far is 9, which is the first value. And again, we're assuming we don't know what the first value is before the loop starts, so we use the first iteration through the loop as the moment where we capture that. Okay? So, smallest is the value, and then we print it, and we go back up, and now it runs again with 41. 41 is not none. None is, there's only one thing that's none. So it is not equal to none. Smallest is not equal to none, or is not none. So this is false, so it skips over here. Then it asks the question, is the value we're looking at, 41, less than smallest? Well, smallest is 9 in this case, and this is 41, so that's false, so it skips that and goes on. So we see 41, we don't take it, and then you can see that this will never become true again. This is pretty much false for the rest of the iterations of the loop. It's false for the rest of the iterations for the loop. So it just is going to run down here and ask this question. And at some point we see a 3, and we run this code, we capture it. We see 74, we don't capture it. We see 15, we don't capture it. So then the for loop skips out. At the end, we have the smallest. And actually, this would be a good technique for the largest as well, because it really is just a technique to put a marker in this variable so that we snag that first number or first whatever as we read and parse through them. So the is and is not operators are very useful in Python. You can think of them as like the double equal sign. They're asking a question, and they return a true or, blank is blank, returns a true or a false. It is stronger. Double equal says, are these things equal in type and value? So just as an example, if I were to say, is 0 equal to 0.0, it would say, yeah, that's true. But then if I says 0 is 0.0, that would be false. So that's because these two are the same value-wise, and these two are not the same type-wise. So is stronger than equals, meaning that it demands equality in both the type of the variable and the value of the variable, and no conversion is done. And so that's just a very strong. Don't overuse is. If you're dealing with numbers or even strings, use double equals, don't use is, because sometimes it gets a little confusing. So use is sparingly. I tend to only use is on Booleans and on none types. I don't use is on integers, and I don't use is on floats, and I don't use is on strings. Just none or true false. And also is not is also an operator. So you just say blah 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 is not none, or blah 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 is not false. Okay, so we've been looping around and doing loops and loops of loops. We looked at the indefinite loops, the while loops that kind of run for a while. The definite loop, and we looked at break and continue as a way to either escape completely from the loop or go back up and discard the current iteration of the loop. We looked at none. We looked at Boolean variables. We have for loops, definite loops, where you've got some kind of a set or a list or some kind of sequence that you're looping through. And then the concept of loop idioms, where you do something at the top, something to each item, and then you sort of get a benefit at the bottom. And so that gets us through iterations.